In this video, we're going to answer a question about sample size in a randomized controlled trial. There are two groups consisting of two types of lens designs, and the investigator wants to know how many subjects they need in order to find a 0.75 diopter difference. But they want to know what that difference is in axial length. So we first need to figure out what is the axial length equivalent to 0.75 diopters. Then we need to figure out what is the standard deviation of axial length so that we can divide that difference by the standard deviation to get an effect size. Finally, a good randomized controlled design has a baseline and a follow-up in 2 years. And we have a couple of data sets that look at where we can determine the correlation between baseline and axial length at 2 years so that we can add that information into our sample size estimation. Finally, we will look up our table and figure out what the sample size estimation is per group for an effect size that we find. Alright, so let's begin. We have a longitudinal database, Vision, it's a prospective trial, and we're going to look at the correlation or the regression of spherical equivalence which is measured in diopters, on axial length, which is measured in meters. And the slope of that is the change of 1 diopter. The slope is a 1 diopter change, and that slope is equivalent to a change in axial length. Change in axial length for a 1 diopter change. And we're going to, because this is a study of myopia, we're only going to look at myopes. And in our database, we have multiple measures per observation. But what we're going to do in this first attempt is we're going to look at, we're going to split the file by years, and in order to just get one observation per subject. So we're going to go to split file, compare groups, and this is years relative to initial onset of myopia. And we're not going to select for particular years, but we are going to just look at years 1 through whatever we have with a reasonable sample size. So we go in, do regression, linear. Our dependent measure is axial length. Our independent measure is init years. No, it's not. It is spherical equivalent measured in diopters. And we find that here we have a bunch of values. We're going to come down here to 1 year after diagnosis of myopia. And we see that the first year we're at minus 0.196. That's the that is the slope of the curve for that's the slope that we're looking for, and it is the change. So let's get rid of some of these guys here. All right. So the slope goes from minus 196, 262, 237, 396, 383. It's kind of interesting. It changes each year. people usually say 3 diopters change is equivalent to a 1 millimeter change in, a 1 millimeter change in axial length. That's a common rule of thumb, which would mean that the slope would be 1/3. So in this case, we don't quite get that, but let's look at our average. Take our average equals average, and that would be that value. I'm inclined not to use the last one because I don't think the n is very great there. But maybe we will anyway, because it's pretty similar to the previous one, so I don't think it's that far off. So our average is 0.2948, 0.295 or 0.29. Now let us look at, let's see, how are we going to do this? We also want to look at the average axial length and the standard deviation of the axial length. So let's go Analyze, Descriptives, and we get this table. Let's put that in our Excel spreadsheet. And let's get rid of all of these guys we don't like. Yeah, there were only 15 cases in that last year. Again, it doesn't look like it messed up too bad. So let's see. Let's do a standard deviation equals STDEV and come down, take the average of those. Now, I suppose we should do a weighted average, but that's, did it count all those blanks? Well, that was inconvenient. Let's try that again. Okay. I could sort and get rid of it, but actually maybe I'll do that. Let's sort. The heck? I don't want help. I want to sort. There we go. Now equals STDEV. Okay. Oh. Johnny. I was taking the standard deviation of the standard deviations. Equals average Okay. I should edit this video and get rid of my stupidity, but hey, there are stupid professors too. So 0.75. So what is our effect size then? Our effect size is equal the slope Oh, not yet, actually. That's the slope. 75% of that slope equals 0.75. This is going to be a very small effect. 75 times that. And now equals this value divided by this value is, around a third of a standard, well, a 0.29 standard deviation difference. That is actually pretty small, and probably doesn't really need to be that small, but this is what the person was interested in. So let's now look at our correlation between the first and the baseline and the second year. Now, to do this, our data is laid out, unfortunately, in a way where it's not easy to do this, because the each subject, each visit is going this way. So to correlate baseline with follow-up, we have to mess with something like that. So that's going to be a little bit of an issue, but not too much. We can do it. So let's go into Analyze, Mixed Model, Linear, ID, init years. We will, now this is the key. We want to choose, I'm thinking, an unstructured correlation metric. Continue, and it's mean axial length with the covariate. No. Yeah. Covariate. Mean axial length is a covariate. Oh. It's lens thickness. Okay, I'm starting to question my ability to do this. I don't think so. Maybe. No. Okay. We can still do it. Mean axial, get out there. Mean axial length, dependent variable, init years, goes there, and I need to turn off splitting the file. Okay. And our model is one of init years. I don't really care about means or anything. It'd be fun to look at them, I guess, but not really required for this. Let's see if they're different. And say OK. Now what we're looking for is a covariance structure that hopefully is going to give us a correlation between those. And it's running right now. It's thinking about it. A little challenging to it, so you have to give it a minute. It's still running. There we go. Okay, it didn't like it. The iteration was terminated, but it still hopefully will give us our correlation. So we want, actually, oh great, so we're going to have to figure out, okay, so this unfortunately does not give us nice plus and minus signs. So let's look at our descriptives, and we're going to count down 1, 2, 3, 4, 5, 6, 7. So we want 8, 9, 10, 11, 12. So we should have 12, and we're going to start with 1 and compare 3. So 8, 9, 10, 11, 12. So that's, we figure that kids coming in have myopia, probably not the first year afterwards, but we're going to look at them at 1 year following diagnosis and compare it 2 years later at 3. So that's 12, 11, 10, 9, 8. So that's 8, 9, and 10. So we're going to compare 8 and 10. So let's see where that is. How about 10 and 8? 10 and 8, 45. So the correlation between the 2 years is 0.45. What's that B say? 0.45, which is a little lower than I might have expected. So let's go back to our Excel sheet. We have an effect size, correlation, 0.45, and SD. Oh, yeah, okay. And so what we'll do now is we will look at our sample size table, file, open. This little sample size calculation table that I made based on slice. This is based on a paper by Fleiss that gives us the sample size. And we'll see, oops, let's move this over here. So we have an effect size of 0.29, let's say 0.3, which is right there. And we want a correlation of, let's say, between 3 and 5. So this is going to be require way too many subjects. Yes. 159 to 131. Now, so using this method, we come up with n equals 131. Now it so happens we do happen to have another data set. And let's see what our estimate is from there. Oh wait, 131 to 159. 131 to 159. 59. And the average of that is so 145 per group. Kind of a lot. So let's do another one. Look at another data set. And this data set was actually from a myopia control study. So a little bit closer to what we're trying to do. That's the good news. The bad news is it's all Asian, Canadian Canadian subjects. So in this data set, this is actually laid out another way, horizontally, which will make our life a little bit easier when we want to calculate the correlation. But there are two eyes. There's a left and a right eye. So we don't want to put that all in the same file, so we're going to split by eye. Split the file by eye. And so let's see. So split the eye by the file by eye, and now we want to do, let's see how many people we have here. This is probably pretty close to the right data set. Okay, so let's do a regression. Analyze regression. Again, it's linear, and the dependent variable is axial length at baseline we're going to do, because we only have spherical equivalent at baseline, so we're going to do that. And here we get a little bit larger value. For the left eye, it's minus 46 versus 43 compared to 29 in average. So that's that. And then we want to look at the correlation. So let's do analyze, correlate, bivariate. And this time we have baseline. And this study followed kids for 5 years. So we'll do 0 and 2, axial length. And this correlation is 9 or 0.9 or 0.8. It's a pretty high correlation. Oops, let's put that down here. Correlations. Copy. Paste. Then we also need to know the standard deviation. So we'll go descriptives, AL0, okay, and correlations are there. or the all right, so there's a little bit of a difference. Now, the good news was the size was different, but the correlations are greater, so, or well, no, the standard deviation is greater. So, I don't know, it could be a wash. We'll see. All right, so our average spherical equivalence equals average is 461. And then we want to multiply that equals that times 0.75. We get 33. Now then, our average standard deviation equals average is that, comma, that. Average standard deviation is 107, and our effect size is equal to that divided by that. 0.31. Well, we're just not getting away from that. Oy vey. One thing, though, is that our correlation is higher. So let's see where we are. We're still at 0.31. We were at 0.29 before, so we'll be looking at an effect size of about 0.3, as we did before. I guess that's kind of encouraging in a way that we went across those studies and we got numbers so close. Completely different studies. Not even the ballpark of similar. But here we can, if we use a correlation, let's see, the correlation was 0.9. You need 48 subjects. I don't think that number is right. I don't see how it can be right. I'm going to go with 63. Make it a correlation of 8. I mean, before we were using a correlation of 4. So we go between 9 and 4. This is still being generous. But a sample size of 63, I think, is pretty reasonable. Equals sample size 63. We could also say 48 and the halfway mark between 48 and 145. It's like 95. So that's our estimate, 63 or 145, or some average in between. That's what we find from these two data sets. The main difference being in the degree of correlation at the different years. So that's it.